This video is intended for Calculus 2 subject with its subtopic Integral and Differential Calculus. Mathematics is fun, so enjoy! Good day everyone! Today I will discuss to you some word problems in our subject Calculus 2. So we were tasked to give 3 examples or 3 word problems of integral calculus and differential calculus. First, I will discuss about integral calculus or the integration. Under integral calculus, we have definite integral and indefinite integral. So, I will give 2 examples of definite integral and 1 example of indefinite integral. Here is the problem under definite integral. So sketch the region whose area is represented by the different definite integral and evaluate the integral using an appropriate formula from geometry. In this problem, you can conclude that calculus is truly integrated in geometry, not just in geometry but also in other branches of mathematics. Letter A, let us sketch 2dx is evaluated from 1 to 4. Here is the graph of the region which has our x are 1 and 4, which is the lower limit and the upper limit of the function. And this f of x is our y. So, y is equal to 2, and our x are 1 to 4. So, we can have a shape of rectangle. So, just by looking at this region or at this graph, we can use or integrate the formula of geometry, which is area for rectangle is A is equal to L times W or L times width. So we have here L, which is 2 or the length, times width, which is 3. So 1, 2, 3. So our area is equal to 2 times 3 is equal to 6. Without using the formula from geometry, we can still get the area of this shape by calculating the definite integral. So we have here 2dx evaluated from 1 to 4, so is equal to 2x, which is the antiderivative of 2, evaluated from 1 to 4. So let us change the value of x by using the lower limits and the upper limits. But first, let us use the upper limits minus the lower limit. So we have here 2, our x is 4 minus 2, and our x is 1, which is the lower limit. So 2 times 4 is equal to 8 minus 2 times 1 is equal to 2. So 8 minus 2 is 6. So they are the same with when we are using the formula from geometry. So 6, 6. Next, let us sketch the region of this function x plus 2 dx evaluated from -1 to 2. Here is the graph of this function. So the question is how to solve or to represent this function into a graph. So first, you have to find y by substituting the value of x into x plus 2. So like for example, we have the value of x -1. -1 plus 2 is equal to 1, which is our y. So this is our y if our x is equal to -1. What if our x is equal to 0? So 0 plus 2 is equal to 2. So our x, or I mean our y, is 2. How about 1? So 1 plus 2 is equal to 3. So our y is under 3. So for 2 plus 2 is equal to 4. Thus, our y is equal to 4. This function is evaluated from 1 to 2. Thus, it limits only in these x values. So, we have a trapezoid. We are done sketching the graph of the function. Thus, we can proceed to calculating the area of a trapezoid by using the appropriate formula from geometry. So the area of trapezoid is equal to A is equal to A plus B, which is A is the base 1 and B is the base 2, over 2 times height. So here in this graph, we can conclude that the first base is equal to 1. Its length is equal to 1, while the second base is equal to 4. So we have here A is equal to 1 plus 4 times height. So our height is 1, 2, 3. So there are 3 units. So we have times 3. So 1 plus 4 is equals to 5 over 2 times 3 is equal to 15 over 2, which is the area of this trapezoid. Y is equal to x plus 2 or x plus 2. What if we don't know the appropriate formula of the area of trapezoid of this function? That is not a problem because we can integrate calculus in finding the area of this function. So here we can get the antiderivative of x plus 2. So we have x squared over 2 plus 2x evaluated from -1 to 2. So first, let us change the value of x by 2 minus the value of x by -1. So here, 2 squared over 2 plus 2 times 2 minus -1 squared over 2 plus 2 times -1. So 2 squared is equal to 4 over 2 plus 2 times 2 is equal to 4 minus -1 squared is 1 over 2 plus 2 times -1 is -2. So 4 divided by 2 is equal to 2 plus 4 minus 1/2 minus 2 is equal to -3 over 2. Change the sign of the subtrahend and proceed to addition. So 2 plus 4 is equal to 6 plus 3 over 2 is equal to 15 over 2. Thus, they are the same with how we calculate the area of trapezoid by using the appropriate formula from geometry. 15 over 2 is equal to 15 over 2 when we are using integration. C, square root of 1 minus x squared dx evaluated from 0 to 1. So it is clear that our graph is a circle because of the presence of this one. So the graph of this function is this one. So the graph of y is equal to square root of 1 minus x squared is the upper semicircle of a radius 1 centered at the origin. So the region is the right quarter circle extending from x0 is equal to 0 to x is equal to 1. So how can we get the area of this one? The appropriate area or the appropriate formula from geometry of a circle is pi r squared. Since our sketch or our graph is the quarter only, so the area of a quarter circle is 1/4 for quarter times pi times r squared. So 1/4 pi r squared is equal to 1/4 pi, which is our r is 1, our radius is 1. So 1 squared is equal to pi over 4. This is the area of the function square root of 1 minus x squared evaluated from 0 to 1. Therefore, by sketching all those three functions, we can conclude that the area of a plane or a geometric figure can also be calculated or measured by using integration. This theorem answers why we can get the area of a certain function, because if a function f is continuous on a closed interval AB, then f is integratable on closed interval AB, and the net signed area A between the graph of f and the interval AB is A is equal to f of x dx evaluated from A to B. Aside from getting the area of a plane by using definite integral, we can also get the average value of a function by integration. This answers how can we get the average value of a function by integration. So we have here, let f be the function defined by f of x is equal to x squared minus x plus 1. So find the average value of f on the interval 0 and 2. Draw the graph of f and show on it the rectangle with base 0 and 2 and area equal to the area under the curve. Let me first explain what is the average value of a function. We have here, this is the original form of the function. And this one is the average value of a function where the rectangle can be at the highest. So the area of this rectangle is also equal to the area of this curve. From the problem, we have function x squared minus x plus 1 and its interval is 0 and 2. So by using the formula of the average value of a function, we have here m of f evaluated from 0 to 2 is equal to 1 over 2 minus 0, which is the b minus the a. Then the f of x, which is the x squared minus x plus 1, dx evaluated from its interval 0 to 2. So 1/2, the antiderivative of x squared is x cubed over 3 minus the antiderivative of x is equal to the x squared over 2 plus the antiderivative of 1 is x. So evaluated from 0 to 2. So 1 half. So let us change the value of x into 2. So 2 cubed over 3 minus 2 squared over 2 plus 2. Originally, it should be minus the value of the lower limits, which is 0. But I didn't put it here because it will still results to 0. So let's proceed to 1 half. So 2 cubed is 8 over 3 minus 2 times or 2 squared is 4 over 2 plus 2. So 1 half. So 8 over 3 minus 4 over 2 plus 2 is equal to 8 over 3. So let us multiply 1 half and 8 over 3. So the result is 4 over 3. So that is the maximum or the average value, of the function. So this is how it looks. So this is the average value of a function. This one, the 4/3. So this is the 4/3 is equal to 1.33 continuous. So this is the 1 and this is the 1.333. So and our interval is 0 to 2. So 0, 1, 2. So 4/3. So the area of this rectangle is also equal to the area of this original form that has an interval of 0 and 2. Let us proceed to the indefinite integral, which is also under the integral calculus, and this is the problem. Find the function of f whose tangent has slope x cubed, minus 2 over x squared plus 2 for each value of x and whose graph passes through the point 1 and 3. So this is how it goes. The slope of a tangent is the derivative of the function f. Thus, this is its slope and the function is this one, which is f is an indefinite integral. So f of x is equal to the integral of f prime of x dx is equal to the integral of x cubed minus 2x squared plus 2 dx. So we have here, let us get the antiderivative of x cubed. We have x to the 4th power over 4, or 1/4 x to the 4th power plus the derivative of negative 2 over x squared is positive 2x. This is y. Negative 2 over x squared can also be written as negative 2x to the power of negative 2. So how can we get the antiderivative of this one? So let us add 1 to the exponent. So negative 2 plus 1, we have negative 1. And let us copy negative 1 to here, negative 1. So next, let us make the exponent positive. So we put it here. So we have negative 2 over negative 1, x to the power of 1. So cancel. The result is 2 over x. 2 over x. So we are done with the integral calculus, and now let us proceed to differential calculus. I have here 3 word problems regarding this topic. So number 1, given a square, how much will the area change if the sides changes by 1%. So, we have here a square, and let us put x to represent its sides. On getting the area of a square, the formula is A, or area, is equal to side squared. In this square, we name its side as x. So we have here A is equal to x squared. Then, the derivative of A with respect to x is equal to 2x. So this 2x is the derivative of x squared. So dA is equal to 2x dx. So dA, our x is 100% for its area, and our dx is 101%, for the change. So we have here 2 times x, which is 100% or equal to 1, and our dx is equal to 1% or 0.01. So 2 times 1 times 0.01 is equal to 0.02 or 2%. Thus, we can conclude that the area will change by 2% if the side changes by 1%. The next problem for differential calculus is this one. A cube 1 inch on each side is to be painted by paint 0.02 inch thick. Use differentials to determine the volume of the paint. So, volume is the formula. Volume in a cube is V is equal to x cube. So the derivative of V with respect to x is equal to 3x squared. This 3x squared is the derivative of x cubed. So dV is equal to 3x squared dx. So for dV, we have x is equal to 1, and for dx is equal to 0.02 for the thickness. So 3 times our x is 1, we have here 1, squared times dx, which is 0.02. So 3 times 1 squared times 0.02 is equal to 0.06 inch cube. So this is the volume of the paint to be painted in this 1 inch side cube. The last problem for differential calculus is this one. A sphere is constructed with a radius of 1 foot. How much of an error can be made in the radius such that the volume will not change by more than 3%? So in the problem number 3 for differential calculus, this is the representation of the sphere which has a radius of 1 foot. In calculating the volume of the sphere, we have this formula. V is equals to 4 over 3 pi r cubed. So the derivative of V with respect to r is equal to 4 over 3 pi times 3 r squared. So let us cancel this one. So the result will be 4 pi r squared. So our dV is equal to 4 pi r squared dr. So our dr, this is dr, is equal to dV over 4 pi r squared. So our dV is equal to 3% or 0.03, while our radius is equal to 1. So 4 pi r squared, or 4 pi times 1 squared, is equals to 4 pi. So here, let us solve 4 pi. So we have 2.39 times 10 to the power of negative 3, which is equal to 0.00239 or 0.239%. This is considered as the largest error that can be made in the radius, such that the volume will not change by more than 3%. So that is. Thanks for watching. Have a great day. Bye.